a 2D type projected surface. But things can not only deposit on this, but they can deposit in it. Or as we have come to refer to it, you can amalgamate things with this mercury electrode. And so he wrote one of the early papers describing this phenomenon. A few years later, this fellow, which I'd be surprised if very many of you know very well, but if you don't, please, if you do, please let me know. Z. Gallus, who I think incidentally was a postdoc with Buzz Adams, again in terms of this community, went off and was really interested in this idea of using mercury electrodes for doing electrode depositions purely from the analytical standpoint. Right, the idea that you have this 3 dimensions rather than 2 dimensions is a great advantage if you want to talk about concentrating. And so in anodic stripping voltammetry, for those of you who remember, if you bias this electrode really negative, so you reduce all the stuff in solution that you might want, and then you sweep positive, so you strip it out, you can get a signal that tells you how much stuff is dissolved in solution. But because you have 3 dimensions, you can dissolve in the volume of this electrode, you can concentrate or really get high signal to noises. One of the things that he noticed early on, and this was published in a rather obscure journal, was that if you did this stripping voltammetry experiment, you started to notice funny things. So, for example, if you tried to do stripping voltammetry of copper, the copper would come out at one potential. If you tried to do stripping potential of zinc in a separate experiment, it would come out at a different potential. But if you tried to do an experiment where both copper and zinc were present, and you stripped them from this mercury electrode, they came out at an unexpected potential, which from a practical standpoint sort of messed up the analytical utility. It represented an aspect that you had to correct for or deal with. And a lot of people thought about this, and again in this community, but that was sort of what this was envisioned or what was going on circa 50, 60 years ago. Fast forward today, what does electrochemistry look like? What are the current frontiers? And these are the sort of talks that you're going to hear at this at Pittcon this week. One of them being given by Dick Crooks, hopefully tomorrow. One of the ideas in electroanalytical chemistry is to do electrochemistry not with mercury or anything like polarography, but to do it with things like paper, and to do things with very simple, inexpensive systems. Again, groups like the Whitesides, Henry's group, Dick Crooks's group have all sort of pioneered the idea of doing electrochemistry and little paper chips or paper sort of devices. And the idea being that this is sort of one extreme of being able to do a lot of analytical tests in a very low-tech, low-cost sort of process and system. Another frontier, if you think about what people are doing in analytical chemistry, is sort of almost the opposite extreme. People are very much interested in electrode materials that look like this. This is sort of a film of very highly crystalline, high pure pieces of silicon, or silicon nanowires here, standing up on a substrate. And groups like the Lieber group and others have shown that these make awesome electrodes for doing very localized probes of different sort of neurobiological systems. For example, here is a neuron where you have different electrodes using essentially these silicon nanowires wired up to look at that action potential, the same thing that they were looking at with my kid Oliver, but now on a very localized scale. Because you can make these high-quality electrode materials and literally place them with, almost atomic sort of precision. And they've done, his group and others have done really tremendous work in looking at asking basic fundamental questions with sort of technologies that look like this, that are really expensive, high-quality materials. And if you think about where we're at today, and this is not meant to be exhaustive in what electroanalytical chemistry is, but in 2 major fronts, there's sort of 2 different directions, and you might think about them being orthogonal. There's this one idea, the Crooks group, for example, pushing the idea of cheap, inexpensive stuff that you could throw away. The other idea is using really expensive technology to do awesome science, but you're not going to throw this stuff away. You're going to spend an arm and a leg to make this. Where we're at today, what this talk is, and where our frontier that we're trying to push, is that these things don't have to be mutually exclusive or orthogonal. Where we are trying to operate is trying to bridge this gap, where that these materials could be made in potentially a way that mimics or is equivalent to this low-cost paper technology, using standard electrochemical techniques that we're all familiar with. And so that's where we're at today, and that's what I'm going to describe. We are very much interested in making semiconductor materials and nanomaterials electrochemically. And we favor a process that's generally electrodeposition, but with a twist. So let me describe what conventional electrodeposition is. If you imagine sort of the simple cell, an electrolysis cell that has been discussed previously in this session, really we're talking about a beaker filled with some sort of solution, and you stick 2 electrodes in that solution. One of them being a counter electrode and one being a working electrode, where this is your substrate that you want to deposit or grow some material on. In this case, we're talking about growing semiconductors like silicon or gallium arsenide or germanium, because these are the things that we know how to do really precise nanotype measurements with. The idea in terms of a standard conventional electrodeposition is if you have some dissolved precursor in solution, you bias this negative so you reduce things at the surface of this working electrode. And so if you take a cross-section of this interface, what you essentially have is a film here in this reduced A material. Let's say this is our semiconductor of interest, that literally plates out or just sort of just accumulates on top of this solid electrode surface, but otherwise this electrode surface is not really doing anything. Maybe there's some templating effects, like maybe that John Stickney or people interested in those sorts of effects would be describing, but essentially we're depositing a new material on top, a new solid material on top of an old solid electrode. This is sort of electrochemistry or electrodeposition 101, and this sort of idea has been used a lot to make semiconductors of interest. For the sake of brevity, I'm not going to go through the whole body of literature, but needless to say, that basic setup is what people have been trying to do or trying to use to make crystalline silicon and gallium arsenide and germanium. And people here in the US, overseas in Europe and in Asia have all been doing this, borrowing tricks from other people in this community like Chuck Martin, combining this idea for electrodepositing silicon and germanium through templates, anodic aluminum oxide membranes, and they can make materials that are nanoscopic or nanomaterials that are similar to what, up front, at least initially, what people like Charlie Lieber are trying to work on. However, if you look at the details in this literature, you know that consistently there's a problem, and there's a reason why people don't use this on a routine basis to make silicon or other semiconductors of interest. When you read between the lines in all of these papers, the materials that you get out are all amorphous. They're not crystalline, they're not high purity, and they're not of good electrical grade, which means in the context of either energy applications or if you want to make some electroanalytical device, these materials are worthless. And if you want them to be useful, you're going to have to do some sort of refining or do some other sort of step, at which point you got to ask yourself, why am I doing this electrodeposition to begin with? The reason for that is not sort of circumstance, and it's not sort of just a coincidence. But if you think about growing a crystal, especially a covalent crystal like silicon or germanium, you got to realize how a crystal forms. And this is where electrodeposition in the conventional sense really goes wrong. Here's a substrate, and here are the building blocks of a crystal. And when you grow a crystal on a substrate, you really have 2 pathways to make that crystal form in really high, large grains. First, there has to be some sort of active dynamic equilibrium between the solid that you're plating out and what's dissolved in solution. If you think about silicon, it's very difficult to ever imagine a solvated silicon atom in water or a common solvent. All right? So effectively, if you're trying to electrodeposit a piece of crystalline silicon, you have no chance with pathway 1. That doesn't exist. The other option in terms of making a good crystal is to have fast atom diffusion. You put an initial atom down, and if it can move to find the right spot on a crystal growth front, then you can make a nice ordered layer. But on a covalent crystal like gallium arsenide or silicon, if you think about the bond energies for this atom on this crystal, these are several orders of magnitude larger than kT. So effectively, if you try to do electrodeposit silicon at room temperature, you don't have this pathway either. And so what you're left with is you're always going to make, in the conventional sense, you're going to make amorphous, unfortunately, not very useful material. Our twist, our hypotheses, or our idea that we're putting forth is this. We do electrodeposition in the same way, a beaker with a counter electrode, but we use a liquid metal rather than a solid metal, with the idea that this liquid metal is going to allow us to make crystals at low temperature, ideally room temperature. And the gist of it is this process, which harkens back to the days of early electroanalytical chemistry, but we sort of refined it and we call it an electrochemical liquid-liquid-solid crystal growth, where the idea is you can electrodeposit some semiconductor on the surface of a liquid metal electrode, but this liquid metal can act not only as an electrode but also as a solvent. Whatever you deposit on the surface can dissolve in this liquid metal, and you can form a solution. From this point here, this solution is a solution like all other solutions that you've ever worked with, where if you keep feeding stuff into the solution, eventually it's going to reach a saturation and then a supersaturation point, and then you're going to make crystals. So the idea here is that if we use liquid metals to do electrodeposition through a process we call ECLLS, we can make crystals controllably with a lot of precision, but more importantly at low temperatures. This is what it looked like in the first generation. Sort of the simplest idea, which again goes back to our roots, is to use a mercury cathode. This is a mercury pool electrode on the bottom of a beaker. This is in an aqueous solution in the absence of anything besides some background salt. This is some buffer to make it a slightly alkaline pH. A mercury electrode is pretty inert towards evolving hydrogen, so you have a really nice cathodic window, and that's what this dotted line here is. If you take this solution now and you sprinkle in some germanium oxide, this is stuff that you would pull out of the ground. This is the raw stuff, and dissolved it in this basic solution. The idea that we were trying to push, actually accidentally at first, but now intentionally, is to reduce this germanium oxide to germanium at the surface of this mercury pool electrode, have it dissolve in that mercury pool, and then form germanium crystals. And so this is what the voltammetry looks like when you sprinkle in some germanium oxide. The species that it's at this particular pH actually is this, but it's dissolved germanium oxide. You do this electrode experiment after a few minutes by biasing your electrode somewhere out here. What you see is that your nice clean electrode becomes basically scuffed over with a bunch of dark brown soot. The interesting thing is this dark brown soot is elemental germanium, which in and of itself is kind of interesting. Because if you do this experiment with a solid gold or platinum or standard electrode, you don't get much of any solid deposit. This whole process passivates after a few monolayers. But on liquid mercury, you can just sort of let your electrodeposition process go all day if you want, and you get more and more dark brown stuff. Now, the interesting thing in the context of this talk is that this is not just reduced stuff, it's crystals. You scrape this dark brown stuff off at whatever potential you're doing this at. The material that you get is all crystalline as you prepare it. You prepare it at a room temperature from a beaker of water, and you're not annealing it or doing anything to it, and you're getting crystals. If you start going with a fine-toothed comb, looking at those crystals, you'll find that the crystals are actually a function of the potential that you're doing your electrodeposition, which is actually a little bit not obvious. It certainly wasn't obvious to us. And what we really noticed is that these crystal light sizes changed the further and further negative we went, or under conditions where we really were driving in germanium into the mercury electrode. What we found is that when we entered this regime out here, when we were really pushing our system, shocking it basically, what we found is that dark brown soot, it wasn't just dark brown random crystallites. What we were getting was these highly ordered, very dense, monodisperse films of germanium nanowires, crystalline germanium nanowires, that were literally being, if you want to think about it, electrochemically extruded from this mercury blob. Okay, this is sort of cross-sections of what this looks like on a microscopic level. This is a cross-section of those germanium nanowire films. In this initial pass, which was done actually by a couple of really talented undergraduates, the subtle features of the diameter were a function of some parameters of the process, but essentially what matters the most is the length. The amount of material was dictated by the time of the electrodeposition. This is sort of when we became very interested, because if you think about that curious result, which you had no business thinking about or expecting up front, but if you think about what they achieved in that beaker, it was really analogous to what people use, what people like Charlie Lieber use, and I apologize, I'm not trying to harp on that group, but for some commonality, I think that analogy works. People like to make nanowires, crystalline germanium nanowires, for example, using processes and equipment that look like this, and through a process that's known as a vapor-liquid-solid crystal growth, where the idea is that they would make a platform, they would dot it with a transition metal, stick it in a furnace here at a really high temperature, expose it to some relatively nasty precursors that then decompose at this hot liquid metal catalyst and then precipitate it out a one-dimensional crystal or a nanowire. All right. The disadvantage with this process is that it's awfully high temperature and involves precursors that you have to spend a lot of energy to make. And our idea was, aha, this might be an in for us, because if you think about what they're doing, it's exactly what we're doing, except we could do it like this. We could throw out all that high temperature chemical vapor deposition equipment. We can throw out all that high energy intensive precursor chemistry, and we can do the same idea but do it with a potentiostat, at least in our case, where we have our working electrode that's now dotted with little micro or nano droplets of liquid metals. And the idea is that we can nucleate or grow individual nanowires at will. And by doing that, we can bypass all this other stuff that we'd rather get rid of. So here is one early pass, not that early, but one pass at it. Long story short, because this community should be more in tune with this sort of experiment than others, we made a little liquid metal ultramicro electrode, starting with a platinum ultramicro electrode, depositing some mercury on it. So we basically got a mercury cap. And the idea is that we could use this platform then to do the same thing that we did before, but on a localized scale. So we could use this. This is a cartoon describing it. We could use a liquid metal ultramicro electrode to try to electrodeposit through this ECLS process a germanium nanowire, maybe one single one. We've done this experiment, or actually Tim has done this experiment several times, and we get, on average, some things that look like this. So here's a before and after experiment. Here we've electrodeposited on a mercury ultramicro electrode, not a single, but relatively few filaments coming off, which end up being crystalline germanium. We've actually done this experiment a lot, and we haven't published this for the reason that we've found that it's actually kind of not quite stochastic, but it's very odd to predict. And our working hypothesis right now is that what you get out of here is highly dependent on the initial stages of nucleation in the system, which we still don't really know how to control, but we have some tricks that we're trying to explore. But it turns out that this system that you can control electrochemically is a really good process for making wires in a rather unusual and unique way. This initial batch of nanowires that we were making with mercury, and just to be clear, they were crystalline, they were very pure, but they were not high quality in the highest sense. They were polycrystalline. And so if you took a high-res electron micrograph of any one of these germanium nanowires, they were all composed of grains of crystalline germanium, but they were more or less randomly fused, which kind of indicates that what you were doing is crystallizing germanium very fast in a relatively small volume. But this is not equivalent to a really high-grade material. To grow better crystals, we have sort of invoked the same ideas that you would to grow better organic crystals if you're a synthetic chemist, and that is to change the solvent. Mercury was the easiest solvent to think of as a liquid metal electrode. The next easiest thing to think about is gallium. Gallium is also a liquid at room temperature. It happens to have the property that at room temperature, which is right here on this reciprocal axis, it's about 100 times better at dissolving germanium than mercury. And so if our whole idea of ECLS is right, this process should work for gallium, and it should produce higher crystalline quality materials. For those of you that are interested, although the electrochemistry is not particularly of interest right now, but this is what the same experiment that I showed you is with electrodepositing germanium on a mercury. This is on a gallium electrode. Gallium is a little bit more active towards hydrogen, so you don't have quite the same window, but it also ends up being a bit more electrocatalytically active for germanium oxide reduction. The net effect is that you can kind of do a cool experiment with gallium that you couldn't do with mercury. Mercury freezes at a relatively low temperature, but gallium freezes right around room temperature. So you can do an electrodeposition process where you're hot, 40 degrees, just above room temperature, and you're using liquid gallium. You could do it at just under room temperature, and it's a solid piece of gallium. And if this process works, then the idea would be with a liquid, you have access to this pathway. When it's a solid, you don't. And so you shouldn't get crystalline germanium. And so this is the results that we got, or that we get. When we do this electrodeposition with hot molten gallium, hot being 40 degrees Celsius, we always get crystalline germanium as our product. When we do it with solid gallium, we always get material that we have very little or no detectable crystallinity. That sort of lends credence to this idea of really doing electrochemical crystal growths. The crystals with gallium, under the exact same conditions where we were extruding out nanowires with mercury, doesn't give us nanowires. What we end up getting are these large crystalline grains of germanium. These crystal grain sizes end up being about 1,000 times bigger. You get a bigger crystal because gallium is a better solvent for growing germanium. Again, we've been thinking about doing this experiment, trying to grow high-quality single nanowires, and now we're going to try to use tiny little gallium nanodroplets. This is what that experiment looks like. And so this is now, I'm thinking, we're getting into a phase where we're not, by any stretch of the imagination, complete or near the finish, but we're now starting to get to something that becomes interesting to think about. Here's that picture again that I showed you, but now this is the experiment, and let me explain it. Our experiment here is to use our wafer as a support substrate for an array of liquid gallium nanodroplets, and that's what you're seeing here. These are prepared in a variety of different ways. We've done this either with very expensive MBE depositions, but these are also very easy to deposit electrochemically. So this can all be done with equipment that looks like this. The idea is that this platform is now great for doing this electrodeposition of single germanium nanowires, but in an array format. And so this is before and after this ECLS process, where the idea here is each one of these nanodroplets is nucleating the growth of one crystalline germanium filament. You can do this on a large scale that's only limited by the source of your substrate and the size of your beaker, and maybe the ingenuity of the graduate students putting this together. The idea, though, here, when we talk about making nanowires in this case, these are not, for lack of a better term, crappy nanowires. These are really pretty good. The nanowires that you see in this experiment, if you'll notice, first off, they're all straight. Straight is indicating that there is some level of order, and that order comes from the fact that these are all single crystals with epitaxy with the substrate. So that wafer substrate is a big piece of a germanium crystal, and we are electrochemically growing off extensions of that crystal. And you can see that directly here. Here's a cross-section of the foot of one of these nanowires on this substrate. You can see the crystallinity of the substrate extends directly into the nanowires that you're growing from equipment. Again, that looks like that at room temperature. These nanowires you can grow with epitaxy and heteroepitaxy, which in the semiconductor community is a big deal. And it's an even bigger deal that we're doing this, again, at room temperature without any other tricks or buffer layers or anything excessive. We are just electrodepositing with a liquid metal and growing a crystal controllably that happens to be seated by the substrate. These tend to grow in a one-on-one direction, so on a one-on-one substrate, they'll grow normal or straight up. On a 100 substrate, they'll still grow in the one-on-one direction, but that means that they're going to grow off at these off angles, as you might predict from just a crystallographic viewpoint. This is growing germanium nanowires on silicon, again showing epitaxy, the ability to grow crystalline materials with some registry with the underlying substrate. And we've been able to sort of figure out that in this picture, there's a lot of little clues that are being told to us, and there's still some mysteries that are still here. We know that these wires, when we try to grow them long enough, they start to bend over, or they kink at some point. That kink, if you take a look at one of these nanowires with, again, a high-resolution electron microscopy, it turns out these kinks don't mean that your crystal stops growing. It just means this crystal has sort of changed its growth direction, but this is still one continuous single crystal. And if you look at all pieces of this, you can track out this being one single crystal. But there's something about how when this crystal grows that causes the direction to slightly change. The interesting thing that we still don't know is that if you look uniformly across this whole array of thousands of wires, whatever that factor is that causes this crystal growth change, it occurs simultaneously at all of these. So it's a function of something about the process, which we are still trying to figure out. One thing I'll mention that everyone always asks me, so I'll cut it up front. In this sort of embodiment, these germanium nanowires, they're tapered. And they're tapered because as you're growing, a little bit of gallium is getting left behind in the crystal growth front. And from a practical standpoint, that means you have some gallium impurities in the wire, and they're also limited in terms of how tall they could possibly get. We've been trying to figure out ways around this. And our answer has really been to move beyond using liquid gallium. We're interested in basically using alloys, or for lack of a better term, solders, to do electrochemistry. So if you think about using gallium-based solders, you can electrodeposit, again, through this scheme. You can deposit arrays of crystalline, nano, and even microwires. Here is a film now that's grown with a gallium alloy. These wires are much larger because the properties of the alloys have changed. And the interesting thing here is that these wires, these materials now have a much tighter aspect ratio, or they can be much longer. and can really look, and if you didn't know any better, could be the equivalent of materials produced by a high temperature process. But again, we're producing it with that. In the interest of time, let me summarize why I think this is kind of interesting. This is interesting because we're talking about doing electrochemistry now with solders, which is not the typical electrode material that anyone thinks about and doesn't publish on, but that's great for us. If you think about what controls this crystal growth process, surface tension matters a lot. In a liquid metal electrode, surface tension means surface charge, or where you're at relative to PZC, which is something that we can control, but we haven't really explored a whole lot yet. We do everything right now in the simplest way possible, but you can imagine an infinite number of waveforms, pulses, potential sweeps, etc., to grow crystals. This represents a moving boundary condition if you think about it. This electrodeposition process, the active spot, is at the top, not at the base. So as you grow the crystal, and the crystal growth rate changes where you're at relative to the diffusion length and diffusion layers. You have a possibility of growing crystals with feedback in real time, and it gives you control that you don't have in any other possible process that I know about. And finally, these are not just materials, but these are wired to an electrode substrate. So you have the capacity to make devices directly, not just materials. There are other reasons why this is interesting. I'll just tell you that you can make other materials besides germanium, but to stress anybody out, I won't go further on that. You can make a whole lot of different materials. But it's not limited to germanium, and that's sort of the key point. So I would argue, and the thesis of this talk, if you want to take home anything, is that a new frontier in electrochemistry is this ECLS process, which is really based on ideas that this community established, but we're trying to twist and take in a new direction. So with that, I'd like to thank the people that did this work, highlighted here in red, funding agencies, and you for your time and attention. Thank you. Questions?
Based on the supersaturation idea and electrocrystallization, going to nucleation of growth characteristics, what are the design rules in a sense? You know that there's got to be some solubility and apply potential of reduction, but in some sense you're kind of limited to really the number of elements that you use as the electrode and what's soluble in those.
Yeah, the design rules, to be honest, we're still trying to figure out what matters the most. Obviously, for growing crystals, whatever your liquid metal is, and I would argue there's a whole bunch of choices if you start thinking about alloys and complex alloys. There's a bunch of stuff buried in the literature, in the solder literature, but I think is appropriate here. You want stuff that has good solubility for whatever you're growing, be it germanium, silicon, etc. So that's criterion one. Well, some of this stuff is buried in the literature. I mean, people have cared, and people in the semiconductor industry have cared a lot about playing around with different liquid metal alloys as crystal growth solvents. It's not immediately obvious, and so there is some exploration and discovery that still has to be done. But coupled with that, though, is also the electrochemical properties. This has to have a favorable, inactivity, if you're going to do everything in water, inactivity towards hydrogen. So you want something that's really dead towards evolving hydrogen. But it helps if this is electrocatalytic for reducing things like germanium oxide or, in a bigger extrapolation, silicon dioxide. Right? Our sort of, I hope, or one idea that we could hopefully one day sort of push is that if you found the right alloy that had the right electrochemical properties and electrocatalytic activity for silicon dioxide reduction, this might be a possible way to do from sand to silicon preparation directly. But it means being able to know and understand both the metallurgical properties and the electrochemical properties. And there's not a whole lot of body literature out there, so we're trying to flesh that out.
I was just wondering, are the germanium nanowires gallium doped?
So yeah, what we see is that if you look at the conductivity of these wires, this one ended up being one that was grown with mercury, but the story is the same with gallium, I believe. These wires come out with some residual amount of these liquid metals. In this case, these liquid metals are dopants. And so these wires, as we're growing them, are conductive at the dopant level that you would that solubility of, say, mercury and germanium at room temperature. That is not necessarily a good or bad thing, but it's a reality that we see. Perhaps this might be a way of controllably making nanomaterials with the right dopant level as prepared. If you could do that, that would be terrific, because you are really now condensing all sorts of processing steps in one. I think that it would be really challenging in this particular process to grow ultra pure crystals without some level of residual dopant in it, but that remains to be seen. We have not. So we are sort of still fleshing out basic details. I mean, believe it or not, everything that I've told you, if you would have asked me this stuff 3 years ago, I would have said none of this stuff would have worked, or these were all ridiculous experiments. We're sort of discovering things by trying to make things as simple as possible. And I think right now we're starting to enter a phase where we can do more advanced sorts of analyses and ask more difficult questions in terms of how do things change as a function of this or that. Right now, we just want to convince ourselves that this ECLS process is what we think it is, a crystal growth process. Yeah, so the motivation for doing those single ultramicroelectrode experiments was to look at the transient explicitly for a single droplet, a single wire, because I think personally that would be very informative, because that's a direct read in terms of how a crystal is growing. What we've done, because we still can't get those experiments reproducible enough, we have done that in terms of looking at arrays. So here's an array of gallium droplets that we've then electrochemically grown these germanium nanowires. These transients change as a function of the pitch and the size. But essentially what we see is that for these larger wires, you eventually reach some sort of steady state growth condition. And here in this case, it's because you have a bunch of different nano droplets that are acting like ultramicroelectrodes in an array. But eventually you can reach a point where you're limited by mass transport to the electrode. But I don't yet know how that impacts whether that causes this particular kink or twist in the crystal that comes out. We're still trying to figure that out. And that's why we want to do those ultramicroelectrode experiments. Yeah, well, there's a size dependence, it turns out. It's a function of several different things, but in some cases, we see that for small little micro or nano droplets, you get the formation that favors this one-dimensional needle or a nanowire. When you make that gallium blob large enough, eventually you transition to a macroscopic domain where your crystal now starts to become basically isotropic. I think what happens is when this becomes large enough, nucleation becomes homogeneous, and now you start growing a crystal in all dimensions. Here, what you see is there's something that preferentially directs crystal growth, be it either the size or the substrate that you're growing off of. I don't know if this is sort of a universal transition, but we do see this sort of effect where size matters.